Hello, everyone. Thank you for joining us for this month's Ceph Tech Talk. And thank you to Dan here for volunteering to provide us content for this month, especially at such short notice. So Dan has a nice talk for us. It's solving the bug of the year. So I'll let Dan go ahead and take it away.
All right, so thanks for the chance to speak here at the Ceph Tech Talk. I will be talking about solving the bug of the year. That's in quotation marks because it wasn't me that called it that, but it was kind of exciting that one of the mean Ceph devs called it the bug of the year, a candidate for bug of the year. So I'm Dan, I'm from CERN IT, and yeah, here we go. So the following is a story about February 20th this year, and the days that followed when our OpenStack block storage went down, how we diagnosed and resolved the outage, and then how we finally solved what would soon to be called, eventually be called the bug of the year. So a quick recap of Ceph at CERN. So CERN, as you probably know, is the European Center for Nuclear Research in Geneva. We have the Large Hadron Collider, which is the largest machine in the world, and we're famous for having discovered the Higgs boson, which is the thing that explains why particles have mass and led to the Nobel Prize for Physics in 2013. Ceph has been a key part of our IT infrastructure since 2013, notably for block storage and CephFS for OpenStack, but also we have an S3 site for object storage, and then we also have some Rados clusters just for custom storage services. In total, we have around 10 clusters with 35 petabytes of raw space at the moment. So just to give some setting, in 2013, we started offering Ceph RBD via OpenStack Cinder, block storage for our cloud. Ceph and RBD proved to be incredibly reliable over the years. We had some very few short outages, mostly related to network connectivity. And over time, more and more use cases moved onto our cloud. Now, as of February this year, there were, just to give some idea of the importance of Ceph at CERN, we had around 500 different shared OpenStack projects using RBD. That's like audio-visual applications, databases, repositories, engineering and physics applications, and more. And then also more than 1,200 personal OpenStack projects that were making use of the block storage. So in total, we had more than 6,000 Cinder volumes, about 4 petabytes raw used. And this was split into 2 pools and 2 rooms, in fact, 1 battery backup room and 1 diesel backup. Here's the timeline of what happened on February 20th, this infamous day. So at around 10:11, when we were at our coffee break, we got a message that the main RBD cluster suddenly had 25% of its OSDs down. The PGs were all inactive, and all IOs were blocked. The whole cloud is down, basically. We started investigating a few minutes later, and we noticed the OSD processes wouldn't restart. And their log files were all showing CRC errors in the OSD map. After a couple of hours investigating ourselves at 12:30, we were checking with the community on the IRC mailing list and the bug tracker. Around an hour later, we understood the problem at a simple workaround at a basic level. And then a few hours later after that, we brought the subsequent rooms up, and we had the service up and running by the evening. So that was the timeline of our big outage. So what happened? But before getting to what happened exactly, I want to give a bit of background about some Ceph OSD internals. So a Ceph OSD, as we know, is the object storage daemon. Normally you have 1 per disk in your cluster. Now Ceph maintains a small OSD map which describes the state of the cluster. And I've given like an example one here for a tiny cluster. It has some information about when the cluster was created, some various flags, and the list of your pools, and also information like the OSDs and when they've been up and running. The OSD map has all of the information needed for clients and servers to perform I/O and recover from failures, so this OSD state information, but also it contains the crush map, which is a description of the infrastructure, the rooms, racks, hosts, etc., and the data placement rules. And the OSD map is shared by peers across the cluster. An OSD can't do any I/O unless it has the latest epoch or version of the map, and each OSD is persisting, saving to disk all of the recent epochs, maybe 500 of them. A bit more detail. So developers rely on some internal functions to encode and decode an OSD map between the OSD Map C++ instance and its serialized form. So the serialized form is the one that you share out on the network, and then you can have it in a class as well in the code. And then advanced Ceph operators are used to using tools like the OSD Map tool to print and manipulate an OSD map. So a bit into our outage now. So how did the actual OSDs crash? At 10:11, 350 of the OSDs out of 1,300 crashed all at the same time with this backtrace. So basically you have handle OSD map, a function, which is receiving, actually looking into the code, you can see what this does. It receives an incremental OSD map from a peer, and then it crashes when decoding it. Making matters worse, the OSDs wouldn't restart, but they have a slightly different backtrace when they try to restart. They call this function called try_get_map, which is actually loading an OSD map from the disk, and then it again crashes in decode, the same place it crashed before, but the path is slightly different. And now we also had a clear indication in the log file that in varlog messages, actually, that there was a CRC checksum error on the OSD map. So we know that the OSD map has been corrupted somehow. And this is what's causing the crashes. We reached out to the Ceph IRC channel, who very quickly pointed us to a related thread that I'll give the materials afterwards, after the talk, but you can follow the links, but who pointed us to a related thread and issue. And this had been seen before, and there was a quick fix known how to recover quickly. So to recover from the actual problem, we extracted a good uncorrupted copy of the OSD map from the mon, so Ceph OSD get map, then a version, and store that, overwrite the corrupted version in each failed OSD's object store. So we use this command Ceph object store tool to set the OSD map in the object store. We did this for every failed OSD across several corrupted epochs, and that brought the cluster back online. And this is the process that took a couple of hours for us to script and get right. 6 or 7 hours of downtime, we were back online. But of course, questions remain. Why did they suddenly get corrupted? And is it going to happen again? So to help with that root cause analysis, we started by looking at a diff of the valid and the corrupted copies of one OSD map. So if you look through this diff of a good one and a bad one, you see some bit flips. There's a bit flip, there's a second bit flip, there's a third, and there's a fourth somewhere, from a 1 to a 0 here, bit flips. Okay? Oh no, it's actually, yeah, anyway, there's 4 bit flips, you can trust me. So we had now some different theories. Why are there bits flipping in this cluster, in the OSD maps? They can have a few different sources, right? They can be memory ECC errors, so uncorrectable memory errors. It could be network packet corruption, or it could be software bugs. Let's go through these. Could it be a memory error? So this was our first theory. We searched all the servers' IPMI error list and DMESC output, which is normally printing something, but there was no evidence of any ECC errors in the memory. And then also, if you think about it, it's not obvious how a memory error could affect so many servers simultaneously. So could it be packet corruption? So TCP checksums on the network are very notoriously weak, and there's a link you can follow to a paper there. Ceph uses CRC32 to strengthen the messaging layer, and it ends up quite reliable. So it would be extremely unlikely to have packet corruption that would hit all the servers at the same time and corrupt the OSD map in the same way. It's not clear how a single checksum error could propagate across the cluster. Confusingly, there were a spike of TCP checksum errors throughout this incident in our router and switch logs, but correlation is not always causation. So the evidence pointed to a software issue, but what exactly? We have some different clues, right? It must be extremely rare because looking at the tracker and the mailing list, there were only 2 other similar reports across the thousands of Ceph clusters out there in the world. We had some initial clues. We have 2 types of on-disk formats in Ceph, right? We have file store and blue store. Only our blue store OSDs were affected. From the other bug reporters on this one, they had mixed flash and HDD clusters, and only the SSDs were impacted. Sage pointed to a recently found race condition in the OSD map code, where with a multi-threaded access to shared pointers that could cause a corruption, but it wasn't. But anyway, we'll get to that in a minute. There's also a feature called OSD Map deduplication that seemed maybe worth looking into, and maybe compression could be it. So when we reported this, Sage got in touch pretty quickly and suggested to disable this OSD Map deduplication. Just a little bit about that feature, because it plays a role later. Recall that each OSD is caching several hundred decoded OSD map epochs. Most of the time between different versions of an OSD map, nothing changes. So to save memory, there's a feature in Ceph to deduplicate the OSD maps in memory. So just use pointers to point to the previous version of the data for each member. Suspecting that maybe there was a bug in there corrupting the OSD map, we set it to false very quickly on the first day. But let's review the rest of the functions. So here's that OSD handle OSD map function. So this is an incremental message arriving. It's processed in this handle OSD map function, and it's pretty simple. It arrives, it checks the CRC of the message. That's one valid CRC. It reads a previous full OSD map from disk and decodes it, which checks the CRC. That's two valid CRCs. And then we apply incremental changes to the incremental changes from the message to the previous full. And then we encode a new OSD map, check the CRC again, and then we write it to the disk. So three CRC checks. So from the backtraces, we know that we receive an incremental map, apply and store it with no CRC errors. We validate the CRCs at least 3 times. But then the next incremental map that comes 1 second later, we try to reread the map that we just wrote to disk, and there's a CRC error now. So this means that something must be corrupting the OSD map after we encode it, but before the bits are written to the disk. We studied that race condition theory that I mentioned, and it seemed unlikely to be related. We checked the OSD map dedupe implementation. It's very simple, and it seemed very unlikely to be buggy. So we started to look more down on BlueStore itself. Some more deep thoughts. So let's look again at that hex diff. There was something that bothered me about this hex diff over the weekend after this incident. And the thing that was strange about it, so if you notice anything here strange, okay, I'll tell you what I found strange was this part here. The address where the corruptions are happening were at almost exactly the 128 kilobyte boundary, a 128 kilobyte boundary in the file, in the object. And that reminded me of something, because we had maybe 3 months earlier enabled compression on the cluster, and we had tweaked some options to set the compression blob size in the OSD to 128 kilobytes. So this was sounding familiar. So could it be compression? I was thinking that, here's our settings. Could it be related? Seemed still very unlikely. But then I got in touch with the other bug reporters. Are you using compression? Yes. Are you using LZ4 like us? Yes. Are you using aggressive like us? Yes. Okay, which OSs? CentOS 7, that's like same as us. And one of the others was using Ubuntu, a slightly old version of Ubuntu, okay, a couple of years old. So now we're sure what the problem is. So here's the story of LZ4. LZ4 is a lossless data compression, very famous. Probably much of the web is compressed with this thing. At CERN, we enabled it in December 2019, primarily because the block storage is highly compressible. We can save around 50% of our space. 5 days, so the bug happened on a Thursday. On the Tuesday afterwards, we disabled LZ4 compression. Before having any proof that it was a problem, we disabled it just to be sure. But how could it be possible that LZ4 could corrupt an OSD map? So let's try reproducing it. When we write, as I said a couple of slides ago, BlueStore is breaking an object into 128 kilobyte blobs and then compresses and stores each blob individually. So we tried splitting our OSD maps into 128 kilobyte blobs, but we couldn't reproduce any corruption. So going deeper, I started learning about word alignment and fragmented memory. So when an OSD map is compressed, it's actually not the thing that in the code that gets passed to LZ4 is not a nice, great contiguous char star array. It's not a contiguous allocation of memory. It's actually jumping all over the place. The Ceph decoders and encoders are very memory efficient, and because of that deduplication as well, you can be sure that your OSD map is actually going to be just a sort of linked list of random locations in memory. And those are often not aligned to the word size of machines. So normally a machine, I guess, would be like 64 bits or whatever. This is not, the alignment times is not matching the word alignment of the machine, which adds further complications. So to reproduce the bug, so we eventually did. We have a new unit test in Ceph, and we could reproduce the bug. You need to take a good OSD map from the disk, decode it into an OSD map class, and then encode it back, and then compress that. And the action of encoding a new serialized map with this like kind of memory scattered, the bytes scattered across memory, and then compressing that, this triggers the bug. So there's a new test unit that reproduces the corruption bit for bit with what we saw in real life. zlib, snappy, and zscd all pass this test with no changes, but LZ4 fails this test. So compressing unaligned memory is complicated. The developer of the LZ4 algorithm has a nice blog post from a few years ago explaining how he optimized access or compression of unaligned memory. So we suspected that this was maybe there's a bug in that area. So we reached out to him on GitHub. Hey, have you seen this kind of corruption before? And he replied, this is Cyan 4973. Nope, that's a new one to me. So we had then a thread with the developer. We tried some different configurations, different compilation options, but nothing changed the behavior. And then Sage kind of came to the rescue. Sage noticed that a newer version of LZ4 on his development box didn't corrupt the OSD map. So he bisected the commits rather quickly and found the exact commit in LZ4 that fixes the problem. So in the end, this was somehow a known issue in LZ4 that had shown up in some of the LZ4 unit testing. And the fix is basically what the fix was is that if LZ4 is compressing from data scattered in memory, it can corrupt the output. If you consolidate it to one single contiguous buffer, it can improve the situation. So LZ4 version 1.8.2 and newer already includes this fix. But alas, CentOS 7 and Ubuntu 18.04 use 1.7.5, so Ceph needs a workaround, or the OSs also need to upgrade their version. This pull request here changes the LZ4 plugin to rebuild the data buffers in contiguous memory. This has been merged to Nautilus, will come in the next Nautilus release. It's already out in Octopus, but it's not yet pushed to Mimic. So if you're using LZ4 compression in these releases, just be slightly cautious. So some comments on actually the impact of this. It's the combination of OSD compression mode aggressive and LZ4 algorithm that triggers this bug. If you have OSD mode compression mode passive, then only the user data in a pool is compressed. When we use aggressive, then BlueStore compresses everything, even the OSD maps or other metadata that the OSD might need to store onto disk. Client data was not corrupted. So of course, this was our concern, was client data corrupted. RBD data that comes in from the OpenStack clients is always written from a contiguous buffer. And also, we have hundreds of ZFS file systems on top of RBD that are doing their own independent checksums of the data, and we would have noticed by now if data had been corrupted, and it hasn't. The corruption was anyway incredibly rare. This cluster iterated through hundreds of thousands of OSD map epochs before it found a corruptible one that triggered the bug. So we learned quite a lot from this. We learned primarily that all software libraries and services can fail. Even though they seem to have worked since forever, these ones that have 59s of reliability can eventually fail anyway. We also learned that too much reliability leads to unrealistic dependencies, which can then lead to a sort of disaster. We had 0 major outages in 6 years of Ceph, and hundreds of CERN apps built dependencies on top of a single Ceph cluster, which was unrealistic. Thinking back to the Google SRE book, there's a story in there about something called the chubby distributed lock service that had a similar story. It almost never failed, and a lot of Google services were built on top of it. And eventually, when it did fail, it took down much more than it should have. So there are lessons in the Google SRE book how to avoid those kind of things. In our case, we plan to introduce block storage availability zones. So we're aiming for 3 or 4 different clusters so that our users can spread their applications across the different clusters, and then they can be more available in case of any problems in the future. So the list of thanks and credits is quite long. We had Theo and Julien working directly with me on the issue the day and the days following, and then lots of colleagues that you can read here in the office building that we were bouncing ideas off of to try to understand what could be the root cause. Everybody agreed that there's no way it could have been a compression algorithm that was corrupting the data. I also want to thank, of course, the Ceph community. In particular, Dirtwash on IRC knew, like, within 20 minutes of our outage, he pointed exactly to the tracker ticket that was the issue. So this got us on the right track right away. Troy and Eric were the ones that had seen this cluster before, and they helped out with clues and comparing symptoms. And then, of course, Sage and Jan Collet, who was the Elsevier developer, for their expert input and fixes. So that's the end of my talk. And I'll be happy to answer any questions.
Yeah, so we got a couple of questions, and one of them was, how did you determine the uncorrupted version to use?
Yeah. So okay. So how did I determine? Okay. So the Mon stores all the versions of the OSD maps. So we knew the epoch. We knew through increasing debugging through the Ceph OSD, we knew which version that the OSD was trying to load. So we knew the epoch number that was stored on each OSD that was corrupted. So we therefore knew which one to extract from the Mon and inject. I mean, the epoch number is kind of like the serial number of the OSD map, and that's the same. It should be the same everywhere on every disk of the cluster, on every Mon of the cluster. I mean, in the midst of this bug, we also wrote some tools to like independently verify the CRC of OSD maps. So those helped along the way, but the short story is that we just extracted it from the Mon where we knew it was good.
Okay, another question. What performance impact did taking the contiguous buffer change have?
That's a good question. I also wondered that. I don't think that's been measured by anyone. If you look at the fix, it simply it checks. It just does buffer list is contiguous. If buffer list not is contiguous, then it rebuilds the buffer.
Okay, and going back to the previous question, how did you determine the uncorrupted version to use? Additional question that came in. So you just went one back from the problem OSD map?
So, I mean, so if the OSD is loaded, I can actually probably just go back to the slide. That'd be exactly. There it was. So this is real. These numbers are not made up. So this epoch number 2.9 million something was the first epoch that was corrupted. So the OSD in the object store for this OSD 666, which is also real, by the way, but I comically included it there. So epoch 2808 was good on this OSD. And when this OSD 666 tried to start, you would get an error that it's loading 2982809 from the object store locally, from its local copy of it, and then it's not able to decode that. So it gets the CRC error when it decodes the copy that it has on disk. So by reading it out from the Mon, we overwrite the copy that the OSD has, and then he can start. But what we found was that then he got stuck on 2810 in most cases. And then so we had to similarly extract 2810 from the Mon and inject it. And we had to do that for probably 6 or 7 different versions of the OSD map. And also, I think later in the afternoon when we were fixing it, there was another series of 3 or 4 OSD maps that caused them all to crash again, and we had to do it again. So there was really something in the data structure that day, something in the weather, something in the crush map exactly that was triggering this bug. It was easier to work around than require people to install an updated library version. So we did both in parallel. I think that maybe the week afterwards, we also opened a ticket with Red Hat to update. And as far as I know, they will have 1.8.2 in one of the CentOS 7 releases very soon, if it's not already there. But at the same time, Nautilus doesn't have a fix for this yet, right? So we did both in parallel. And then there's a question about compression in general. General question about compression in Ceph. Is compression something you would only run on SSD OSDs, or is the performance penalty small enough to run on HDDs? In fact, I think that your intuition is backwards. I mean, hard drives, HDDs are so slow that the CPU could easily compress the data faster than what the hard drive can absorb and write the data anyway, and also for decompressing the data. So often, when we use compression in other areas like Ceph or other areas, we see a performance increase in bytes written per second. Yeah. Brian's asking, when is it expected to make it to Nautilus? It's been merged to Nautilus, so it'll be there 14.2.10. Yeah. And then Victoria's asking, are all the clusters at Nautilus? Nope. We have, so out of 10 clusters, 2 are still in Luminous. We have a CephFS cluster that we're still waiting to upgrade. We're waiting for some last bug fixes before we'll upgrade to Nautilus. And similarly, S3, we're waiting for the last, just a few little bugs to be fixed here and there. And then Anthony, I'm not sure I understand the question. Contrast replication plus compression to EC. EC plus compression.
Yeah. With the goal of having more efficient usage of the underlying raw storage, is why we do compression, right? And it's also the same reason we do EC. So I was just curious about thoughts of one approach versus the other, or combining them.
I think if you have, so for RBD, I think that doing both is a good idea. There are lots of gotchas along this though. So the reason why I say for RBD is because you often have like big 4 megabyte or 8 megabyte objects that are easy to split, and then easy to split into things that are still relatively large, and then you can compress them easily. With CephFS or S3, if you have smaller files, then maybe it doesn't pay off because you have minimum sizes that you have to fill with zeros to pad out small files or small objects. Now, the other gotcha about compression on RBD is that I haven't observed this myself, but there were theories that because RBD is normally, like the actual workload is normally 4 kilobyte writes or maybe 64 kilobyte writes, because it's usually small changes to the blocks. You're not in fact writing 4 megabyte objects all at once. You're just writing small changes. So the fact that you're just doing those small writes, it might have an impact. And I don't know what the implementation does, if it reads out the whole chunk and then writes back, or if it just somehow writes a small extent. But the fact that RBD does small writes anyway might over time kill any kind of space savings that you might have thought that you're earning. Yeah. So, question from Jared, just asking for clarification. It was the storage nodes packet version of LZ4 that caused the problem, not the client side version. Correct. It's the version of LZ4 running on the OSD servers. That's important because the data is compressed. In the case of BlueStar compression, the data is compressed by the OSD itself. Brian's asking if we're still using compression on the object storage clusters on the object clusters too. So after this, we disabled compression everywhere. We haven't re-enabled it yet, but I would re-enable it. I would re-enable it in passive mode and enable it per pool. I don't feel comfortable compressing the OSD maps anymore, so I wouldn't use OSD compression aggressive anymore. Did the version running on the Mons matter at all, assuming no Mon OSD colocation? The Mon would not have corrupted the OSD map because the Mon does not use LZ4 to compress. I think that, so the Mon uses RocksDB and the Mon can compress using RocksDB compression, but I think that that's snappy in all Ceph configurations. I might be wrong. I hope somebody can correct me if I'm wrong. And I think it's off anyway by default. And by the way, well, I think that when the Mon would get the OSD map, it also wouldn't use these encode decode functions like the OSD does. I think it would just get the blob and write it. I'm not sure about that. I could be completely wrong about that. Yep. The sun's coming in now. Any other questions?
Looks like we're clear in chat. All right, I think we're good.
Excellent.
All right, Dan, thank you for your time and sharing with the Ceph community for another Ceph Tech Talk. And this will be, of course, recorded and put up on YouTube. So thanks, everyone.
Okay. Thanks a lot. Thanks for the feedback on the talk, too. Nice to meet virtually with people somehow, anyway.
Yeah. All right. Thanks, everyone. Bye.
Okay. Bye.